So those transient response characteristics have exact analytic solutions for first and second order systems. And also you could go up from there, but we typically don't. Because higher order systems, it turns out, have response characteristics that look a lot like first and second order systems. Often. It's not universally true, so you have to be a little careful. But we typically don't go to higher order for defining these. So for instance, we're going to come up with an expression for the settling time that is true for a first order system in terms of the time constant of that system, and for a second order system in terms of the damping ratio and that natural frequency. So we can predict these variables without having to do a simulation or do any measurements of the system. So it's convenient to calculate. So first order systems without zeros, so we don't really have a lot of background knowledge to understand what that is. Without zeros means that it no derivatives of the input of u. There's no derivatives of the input. These systems have transient responses characterized by a time constant tau that appears in the total response as something e to the minus t over tau plus something, right? We're familiar with that. This came from our homogeneous solution, and this comes from the particular solution. The transient exponential decays such that in 3 time constants, only 5% of the term remains. So in 3 time constants, we've got within 5%. In 5 time constants, less than 1% remains. So those are some pretty good ways to think about it. There is neither peak nor overshoot for this type of response. So it never peaks. It doesn't overshoot the steady state value. It doesn't peak. It just decays to it. Okay. However, the rise time for this system is found from the solution to the first order input-output ODE for y of 0 equals 0, which is just this, right? So what this looks like is doesn't quite hump like that. Yeah. It's not great, but it could be worse. So it's headed towards some steady state value. We're calling KB0, and it's doing so exponentially. The rise time is, by definition, the duration of time such that it goes from, the output goes from 10% of its steady state value to 90%. So that's from, say, there to, say, there. So we need to know this time interval. So I'll call this T1 and this T2. So we need to know, we know y of T1 and y of T2, so we need to back out what the times are. The first of these yields, so if we want to know when it gets to 0.1 of the steady state, notice that we can cancel k, b naught, so these cancel, and we're left with this expression here. You can add this over, subtract this over, and you end up taking the log, natural log of both sides. T1 equals negative tau natural log of 0.9, which is approximately 0.1054 tau. Solving in an analogous fashion, we find that T2 is 2.3026 tau. The interval then is T2 minus T1 equals 2.1972 tau. So what we often say is that the rise time for a first order system, so it's equal to tau times the natural log of 9, but we're lazy and we don't usually actually compute the natural log of 9. So we just say that this is approximately equal to 2.2 tau. So the rise time is about 2.2 time constants for a first order system. If you have a second order system, can you use this equation for the rise time? No, you cannot. So there's no time constant for a second order system. At least not in the same sense. So finally, the settling time can be derived in a fashion similar to the rise time. So you have to figure out when the value gets to 0.98 times the steady state value. You plug it in and do the same analysis, and you end up with the settling time being equal to negative tau times the natural log of 0.02, which is approximately equal to 3.9 tau. Sometimes we'll say 4 tau. So settling time is about 3.9 time constants. Not too bad. I will say that for first order systems, we do talk about these terms, these response. Thanks. I heard that people say that so that like an evil spirit doesn't infest itself in your soul.
You're sneezing out this evil spirit.
Oh.
Oh, I thought it was supposed to during the Black Plague times, people that would sneeze, they thought we're going to get the Black Plague, so they were going to die. So they were trying to bless their souls before they died.
Yeah, that's what I.
It's
also that people say your heart stops, so they bless you when your heart stops. So that way you come back from your sneeze.
It's a lot of theories. I don't know. I don't know what to think.
We just say bless you because Gesundheit sounds too Nazi-ish.
It is funny how in American culture we have associated a lot of things German with Nazi, which is too bad, really. I think that it would feel weird to be German, I feel like, in America sometimes, because we pretty much associate anything that sounds German-like with anything that's like
the rest
somewhat
of the world
would be
does
Nazi.
too, but we have no shame.
We have what?
We have no shame.
We have no shame.
Yeah.
Yeah, we also tend to be very ignorant of other cultures. I mean, in my own observations of myself, I will say that is true.
Could you go back real quick, just as rewrite the
Yeah.
rise time?
Sure.
Just tau.
So with the first order system, notice that we're writing it always in terms of the time constant, and oftentimes the time constant is just used instead of talking about rise time or settling time, because people have a pretty good feel for, okay, in 4 time constants I'm pretty close, 5 time constants I'm really close, that kind of thing. So it's less often used to characterize the transient response.
So given, like, say you weren't giving anything but tau, you should be able to back out a rough graph of the system's behavior
Totally.
with just that.
Yep, because you know it's first order, and so for a step input, its response should be this, which looks like that, right? And so the only thing that changes on this graph from system to system is what this value is, the steady state value is. So that's just the vertical scaling, right? And how fast this exponential decays. So those are the only 2 things that change on this graph for any first order system. Yeah. So first order systems are great. Their transient responses are so easy, right? They're just exponential decays. Second order systems give us, all we can handle. So second order system transient responses are characterized by a natural frequency, omega n, and damping ratio zeta, which you guys have now experienced quite a bit in your homework. By the way, new homework is up. It is, it's just in chapter 3, so I have more problems from chapter 3. I think it gives us a little deeper into the chapter. The rise time TR does not have an analytical solution in terms of omega n and zeta. However, figure 3.11 could be developed numerically because I am capable of that. You're welcome. You can find this graph other places too. But you can look up your damping ratio. Say you have a system that has a damping ratio of 0.68, say. You could follow that up. It intersects there and follow it over, and you would say, okay, that looks like it has a dimensionless rise time of 2.1. So what you would say is 2.1, or 2.2, either one. 2.1 equals the rise time times the natural frequency. And if you know your natural frequency, you can divide it over and get your rise time. So that's nice. It's an actual, honest-to-God engineering chart that you guys can look up values on. I know. It's old school right here. It's good, though. I like charts. I think they're fun. So, good. So that's the rise time. The peak time has the following simple expression. It's just pi divided by the damped natural frequency, which is about as easy of an expression as you can hope for a second order system. The percent overshoot is related directly to the damping ratio. So the peak time is related to the natural frequency and the damping ratio. The percent overshoot is related directly to the damping ratio. So percent overshoot as a function of the damping ratio is this, which is kind of gross, but not too bad. And then you can solve this equation for the damping ratio in terms of the percent overshoot. So you can go one way or the other. Give you both expressions. This one's used quite a bit. It's nice. So a lot of times you'll say system is this percent overshoot. You might also, same system, you might say, this is the damping ratio is this. They essentially are the same thing because you can compute one from the other. So if you specify one, you specify the other. Finally, the settling time isn't too bad either, 4 divided by zeta omega n. And these expressions are really nice because you can use them to do something a little less theoretical. So some of you guys are probably happy about this. And in your homework, you're going to be doing this. So you might have a second order system response, and you want to know you want to estimate what zeta and omega n are for the system. Why might you want to do that? You might want to predict how the system's going to respond, your measurement system's going to respond to other types of inputs. So you put in a step input and you get out a certain response. You got to be able to back out what omega n and zeta are. If you figured that out, omega n and zeta, then you can characterize your system. You could do simulations of your system. You can solve for different types of inputs. It's really useful. So that's one of the things that we will want to do is to measure essentially what the transfer function or the input-output differential equation looks like, which is essentially determined by what zeta and omega n are. So we can measure zeta and omega n indirectly from the system response. And these relationships here give you the gate to that analysis. So I'm going to let you guys work on it a little bit, and we'll go from there. Yeah.
So where it says percent overshoot and it says 100 EXP, is that supposed to be exponent like E, the natural number E?
Yeah, so sometimes we don't want to put the exponent of E in the exponent because it's big, like in this case. So it doesn't fit very well into an exponent. So we'll just write out EXP.
Just double checking because I know you do that in MATLAB.
Yeah, it's similar notation to the MATLAB notation. And in this class, it always means the number E. What is it called? The natural number? Natural number E?
It's like 2 point.
No one knows.
A number
He uses it
operator.
every day, though.
Some kind of fancy
It's
It's
a
thing.
2.06, I think, right? Or 2.2?
It's either one's or 2.7.
That was 2.2.
2.2.
I don't know.
Okay.
You guys have calculators. You can figure it out. Tell me what it is. I know it's 2 point something.
718.
2.718?
Yes.
That's what I thought it was.
Those guys.
All right.